Well, there are some special relationships between load and shear and moment that we're going to talk about now. And we're going to learn how to draw shear and moment diagrams, or at least just shear diagrams, primarily by inspection, and then how to use what we have in the shear diagram to draw the moment diagram. So just remember the positive conventions for shear and moment. I would again look carefully at how you define the shear and moment equations, and some of this part here about shear and moment diagrams. We're gonna plot them, but we're going to again draw a lot of it by inspection. I just want to start practicing that, and you can catch on and see how to do it. Alright, so here is a simple one. It has two forces. It's just a beam with two forces, and there's going to be a reaction at each end. What it says here in the drawing is P is equal to 800, and this one is equal to 800. There's a distance 5 here and 5 here, which makes that middle one distance 2. There's going to be a reaction. I'll call that AY, and another reaction over here at BY. Okay, this happens to be a symmetrical or a symmetrically loaded beam, and so that we could say that AY equals BY, and they're both equal to 800. When that happens, we can draw the shear. When we have all the forces defined like that, we can draw the shear diagram by inspection. What shear does is it moves in the direction of the applied or the reaction force. So if this force is going up, shear goes up. If this force is going down, shear goes down. In between, shear does not change. So let's just go ahead and draw it. Shear goes up by 800, or up to 800. So that's 800. Between these two forces, it has no change, and it goes down 800 where that applied force is. Between these two forces, it has no change, and so then it goes down another 800 when it gets there. No change again, and then goes up 800 when it gets to the other side. So here we have the shape of the shear diagram. The moment diagram will change linearly if the shear does not change. So in other words, if shear is uniform or not changing, moment increases or decreases uniformly or linearly. So that means from here to here, it goes up in a straight line. Between these 2 points, because there's no change in the moment, and because moment is 0 here, that means there's no change in, because shear is equal to 0, there's no change in the moment. Here, because shear is now negative, that means moment is decreasing, and it will decrease linearly from this point back down to 0. And you say, how do I know all that? Well, there are some rules which we're going to talk about. Alright, and one of the things that we'll recall, or what we'll learn here, is that the area here is equal to the change, which is equal to delta moment. The area here is also equal to the delta moment. So in this case, delta moment is going up because this is a positive shear. In this case, the change in moment is negative because this is a negative shear. All right, let's talk about the rules, and then we'll get to some magnitudes. All right, so what I call this part is shear and moment diagrams are predictable. Shear is steady, meaning it has no change between applied forces. There's a discontinuity in the shear that occurs between or at applied forces or at reactions. Shear moves in the direction of the applied force or the reaction. And if you have a uniformly distributed load, shear will change linearly. So if the load is going down, which often it is, shear will decrease linearly. Moments are going to be positive or negative depending on how they're prone to bending. There's going to be a discontinuity at each applied moment, and it will have if you have a counterclockwise moment, it causes moment to drop. A clockwise moment causes moment to rise, and those are discontinuity in the moment graph. It will be linear or uniform or not changing between forces, and it changes by x squared during constant or uniformly distributed load. And here's something that's key. The maximum moment occurs where the shear is equal to 0. And what I just showed you before in the prior picture, positive shear causes increasing moment, negative shear causes decreasing moment. Then a couple of things we're going to use here. We're going to use these understandings of how this thing goes. And I'd like to talk about this one in the next slide, where we have the area under the load is equal to the change in shear. But the ones we're going to use to draw the shear or draw the moment diagrams is these two. We're going to say that the slope of the moment diagram is equal to the magnitude of the shear. And the change in the moment diagram is equal to the area under the shear. And again, we'll use those going forward, but you might want to refer to this until we get used to doing this by memory. All right, next thing I want you to focus on just a little bit are these very simple examples, and this will be provided for you, or this is part of your documentation set here. Okay, so again, the shear diagram will change in the direction of the force. So if you have a reaction here, shear goes up. If you have a force applied, shear goes down. If you have a reaction over here, shear goes up. If shear is above the line, that means it's positive. That means moment increases linearly. If shear is below the line, meaning negative, then moment decreases negatively. If there are some forces, just like before, but you have a counterclockwise applied torque or moment at the end, then where that moment is applied, again, this is not a free moment. You can't move it around the shaft. It has to be applied right where it's shown in the picture. In other words, the shear doesn't change, but the moment diagram will go up if there's a clockwise moment. It goes up that magnitude, then it follows the same pattern. If there is a uniform load, uniformly distributed load going down, you'll still have some reactions at the ends, which means that the shear will go up, and it also goes up at the end because those are both going up, and then it goes down, decreases linearly between those two forces. This is now a straight line, which means that the moment becomes a quadratic. Where the shear crosses the x-axis is where we will find the maximum moment. In a similar way as here, if we have a clockwise moment applied at the beginning of the beam, or any place on the beam, wherever this is applied, you'll see a step up to that magnitude. I don't think we're going to have any uniform loads that are applied upward, but if it does, the load will increase linearly. Most of the time we're going to have loads that are pointing down, which means that shear will decrease linearly like this. All right, I'll let you go through the rest of these and you can just kind of make sense of them. What I want to do, I'll let you make sense of them for a little bit, and then I'm going to talk about something else in just a second. Well, we are continuing in this relationship, or understanding the relationship between load and shear and moment. And I just want to refer you to this equation from our book, and it says that the integral of the load is equal to the change in the shear. All right, let's just look at this one right here. This is one single load, so between these points there is no load as a function of x. There is no load at all, in fact. So that means the load as a function of x is equal to 0. Therefore, the change in shear is equal to 0. So in this first one, the change in shear is equal to 0. Over here, this one does have a load. It is 50, whatever it is, 50 newtons per meter. And so the load here as a function of x is going to be a constant. And it's going to be a negative because these guys are pointing down. So that says that load as a function of x is equal to negative 50. Therefore, the change in moment, or change in shear, is going to be the integral of 50 dx, negative 50 dx. And what we have already discovered is that it begins with 250. So I'm just saying shear minus 250 is equal to negative 50x. All right, how about this one over here on the bottom left? Here this increases linearly until it gets to 50. And so the slope here is actually, because this is 50 and it takes 10 meters to get there, the slope here is equal to 5. Now, but our weight, or our weight as a function, or sorry, our load as a function of x is going to be negative because these are going down. So I'm going to say that load as a function of x is equal to negative 5x. Okay, so then I have my integral here. Delta v is equal to the integral of 5x dx. Change in shear is equal to the integral of minus 5x dx. So that's going to be, in this case, because it started with 83.3, it'll be shear minus 83.3 is equal to minus 5x squared over 2. Okay, and then the last one here. Again, they have the same slope. It is 5, negative 5, but it starts with 50. So in this case, the load as a function of x is equal to 50, let me put it this way, is equal to 50 minus 5x. And so the change in shear is equal to the integral of 50 minus 5x dx. And again, it starts with 166.7, so shear minus 166.7 is equal to 150, I guess that's just 50x, sorry, 50x minus 5x squared over 2. Anyway, that helps you use the load diagrams to come up with a description of the change in the shear, which might be helpful or handy.